project, my robot is designed to locate, pick up, and transport metal discs in a controlled environment. Using its crane arm equipped with an electromagnet, the robot identifies and securely lifts each disc. After gathering each disc, the crane navigates back to a specified area where it releases it, completing the task. The robot's actions simulate essential tasks for Mars missions, where robots may need to collect samples, transport resources, or handle equipment for scientific and logistical purposes. Effective object manipulation and placement are critical for establishing Mars habitats, especially in locations hazardous to humans. This project demonstrates a capability that would be foundational for sustaining long-term exploration and development on Mars. The robot relies on its gyroscope to maintain orientation and navigate effectively towards large objects. Once positioned near a disk, it activates its electromagnet to securely pick up the object. After lifting, the robot uses its orientation data from the gyroscope to retrace its path and approach the designated drop-off area. At this location, the electromagnetic disengages, releasing the disk precisely where needed. Once more, the code is nothing more complex. Initially, the robot will drive forward with even left and right speeds for 16 rotations, which is how long it takes for it to reach the back of the grocery store on the map. The motor on port C controls the base of the crane arm, and with the specifications, it'll rotate 45 degrees to the left, which will put it directly over the magnetic disc on the floor. It will rest for 1 second because motors are finicky here. Running the motor on port E at 50% is what turns the electromagnet on, causing it to pick up the disc. It will rest again. It'll return the arm to its original position directly in front of the robot, still holding onto the magnetic disc because the electromagnet is still engaged. It will backtrack its 16 rotations in the negative direction because of the negative speeds. It will stop, turn to the left in place because of the specified negative 15 speed, and then it will move forward for 3 rotations, which will put it into the landing zone on the map for the red disk, at which point it will then disengage the electromagnet by setting that motor the value of 0%.
The robot starts off with an objective of reaching the back of the store, and to do this it sets both motor values to 20 and carries forward for 16 rotations. It's going to veer slightly off course because of the weight of the arm in the front, as near as I can figure, and later movements will accommodate for this error. It actually is beneficial in the end, because when it reaches the back of the store with the central red disc, it rotates the arm 45 degrees to the left, engages the electromagnet, and reverses its original path. The electromagnet value does not change during this, which is why it keeps engaging with the red disc. It will carry it back to its starting location, at which point it will stop. It will turn left, carry forward, and deposit the disc in its color specified point.
One of the main challenges in this project was motor calibration, as the robot frequently veered off course during navigation due to the weight of the crane arm in front. This misalignment affected the robot's ability to reach and retrieve discs accurately, impacting the precision needed for the task overall. To address the alignment issue, I recalibrated the motor speed slightly to ensure consistent forward movement. By carefully adjusting the motor settings, I was able to improve the robot's path stability, at least slightly, allowing it to stay on course and complete the task of the object manipulation with greater accuracy. This project highlighted the importance of precise motor calibration for reliable robotic movement. Working through the motor alignment issues provided valuable insights into refining motor control, a critical skill for developing robotic systems that can perform precise and consistent tasks in complex environments.